So far in this course, we've covered kind of an astounding amount of ground given the limitations we've placed on ourselves. We've only allowed ourselves to deal with equilibrium states of systems, and we've only allowed ourselves to deal with quasi-static changes between those equilibrium states, meaning that all of the thermodynamic parameters were changing relatively slowly with respect to time in order to accomplish all of the things that we wanted to do. And that's allowed us to deal with phase transitions and heat engines, all kinds of really interesting phenomena, but not enough phenomena, right? We can't deal with, for instance, heat diffusing across a piece of metal, or we can't look at convective processes like the wind blowing. We really need to broaden our scope if we want to be able to look at a whole other range of phenomena that might be of interest to us. Remember that I said that thermal physics is something where we should take a phenomena first approach, meaning that we have some phenomena that we think of as thermal, and we create theories in order to describe those phenomena rather than trying to look at the consequences of a particular set of equations that we write down right at the beginning. We've reached kind of the end of where we can get with that original set of equations or set of rules that we wrote down for classical thermodynamics. And so now it's time to deal with something that I call thermal flow, which is really just all of the ways that we use classical thermodynamics in order to build dynamical theories. Okay, so how do we do that? Well, the idea here is that we have a variety of thermodynamic control operations. And so far, it's always been the user's prerogative to use those control operations on various parts of the system. Now, we're going to take that prerogative away from the user and say that these systems merely undergo, for instance, thermal joins at some rate. So they happen so every so often. And no one has to choose for that to happen, and no one can choose for it not to happen as long as these systems are in contact. So let's think of one sort of simple example. We'll have a bunch of small boxes and we'll place these in an infinite one dimensional line. And after every so long, these boxes will undergo thermal joins with each other. And as we'll see in a moment, this will allow heat to move across the sample. And I say move because we don't really have that notion yet, but we'll get there. Okay, so that's the basic idea of what we're doing. And I've used the idea of energy moving across, internal energy, but we could do this with particle number or in principle with volume. We could do this with a whole host of thermodynamic quantities of interest. Nevertheless, let's stick with, for this video with the example just of energy moving in this 1D line. Okay, so each of these boxes is going to have an energy U. So this can be U1, U2, U3, U4. Notice we'll have U0 and U minus 1 as well. So I'm indexing these boxes by a spatial location. Excellent. Now, over here in the corner, let's remind ourselves what happens when we take the thermal join of two simple systems. And just for ease of use, let's imagine that each of these contains an ideal gas. So in that case, we have U, say U1 prime over N1 is equal to U2 prime over N2. This is just the condition that the temps are equal. And we have that U1 prime plus U2 prime is equal to U total, which doesn't change. Now, if we combine those equations, what we find is that U1 prime, for instance, is equal to N1 times U total over N total, or N1 plus N2. And a similar equation holds for U2 prime as well. Now, one more simplification, just to make our lives as easy as possible in this problem, let's just assume each of these has the exact same number of particles, n. So we can assume that when we have a join of two boxes, the ends here will cancel out and we'll just get some simple factor. In this case, it would be 1/2. Okay, great. But the problem is that we can't just have all of these join every time step. So we're going to introduce these discrete time steps. But if they all joined every time step, then after exactly one time step, they would all have exactly the same energy. And that seems a little strange, right? This is an infinite line. So in principle, these boxes might be spatially very far away from each other. We should limit the number of boxes that can interact during a single time step. It turns out that there are a ton of different ways that we could possibly do that, but here's one. So at time, let's say t equals 0. So t is going to be an integer here. We're just going to have all of the boxes hanging out. Okay, and this can be the j equals 0 box. This can be -1, 1, 2, 3, 4, -2, and -3. Now between t equals 0 and t equals 1, we'll have some of the boxes touch. Okay, so we're going to bring together -1, 0, and 1. Then we'll bring together, let's see, 2, 3, and 4. And we'll bring together -2, -3, -4. Good. So that'll lead us to t equals 1, where they're all back hanging out again. Okay, so now these clusters of 3 have been thermally joined. So what we're going to do next is we're going to have -2 join with -1. 0 will stay by itself, and then 1 can join with 2, and so on. Okay, so we'll have -3 by itself, and then these two will join. 0 by itself, then these two will join. 3 by itself, and so on. And then that'll lead us back to t equals 2, where we'll have them all hanging out again. Okay, so now it could take us quite a long time to go through the math of what happens here to every single box. Let's focus on just a couple. So for instance, j equals 0 and j equals 1. Okay, so what happens to the j equals 0 box? Well, let's say that at time 0, it has u of, so hang on, at t equals 0, it has u0. That's going to be for the time step. And then position 0. Good. Okay, at time 1, well, we'll have u of 1. Let me just make sure that's clear. 1, 0. And we can figure out what that is in terms of the energies one step before. And the way to do that, which I didn't quite denote down here, is to notice that what we get for U1 here would just be the average of U1 and U2. When it's 3 boxes being joined, we'll still get the average in this case because all the ends are equal. So we actually just get 1/3 times the sum here. So U0 minus 1 plus U0, 0 plus U0, 1. Excellent. Okay, let's move up here to continue. So at t equals 2, well, notice that it's just the same. U 2, 0 is just equal again to 1/3 U0 minus 1 plus U0, 0 plus U0, 1. Excellent. And we'll basically repeat in this kind of two-step pattern. Okay, now let's deal with the j equals 1 case. Notice that something extremely symmetric will happen to the j equals -1 case. Okay, so let's do it. At t equals 0, nothing interesting to say u 0 plus 1, sorry. Then at t equals 1, we actually just have that these all have the exact same amount of energy because they have the same number of particles. So we get this expression, just as we did for the j equals 0 case. So we get 1/3, oops, let me be really clear here. We get that u of 1 is equal to 1/3 u 0 minus 1 plus u 0 plus u oops, 0 1. Excellent. Now what happens next is kind of interesting because j equals 1 is right here, and it's going to join with j equals 2. But one step before, j equals 2 was joined with 3 and 4. What that means is that at t equals 2, we would have the following. So we would have u2, 1 is equal to 1/2 u1, 1 plus u1, 2. And then we'd have to expand this. That expansion gives us 1/6. And then let me just even represent it as a sum. It'll be the sum from k is equal to, well, in this case, we have to go from -1 all the way up to 4 of u 0 k. Excellent. Okay, I'm going to clean up the board and bring this all up so that we can take a look at it, and we'll continue. Okay, here I've summarized what we found on the last board, except I've made a couple of changes. One of these is that instead of looking at t equals 0 to t equals 2, I've just noticed that we could generalize this to t plus 2. Now, I guess I should note here that t really should start at, what should it be, an even number, I guess. So this doesn't quite work if t is odd, but that's all right for our purposes at the moment. I've also introduced some scales. So rather than these just being integers, I now want to think of them as having units. So now we're measuring this in terms of a small time step tau and a small length step xi. Excellent. Okay, so I'm going to start writing some things out, and let me start for these cases, the cases where j was a multiple of 3. Excuse me. So what I want to do is make this look something like a first derivative in tau. So what I can do is this. So t plus 2 tau 3jc minus, well, I want to look at something that's close to this in tau, which in this case would just be t tau 3jc. Notice that this differs by 2 tau, so I need to divide by 2 tau here. Excellent. But now I can plug in my expression from up there here. So this is just going to be equal to, well, let's see. I'll get 1/3 times this term, plus 1/3 times this term, plus 1/3 times this term. But notice that this term here matches this term here, except this is attached to a -3/3, or -1 if you want, which means that this will eventually be a minus 2/3. But if I pull the 1/3 out, then it'll be a minus 2. Okay, so just to be clear, this is now 1 over 6 tau times u t tau 3j minus 1 c plus u t tau minus 2 u t tau 3j c plus u t tau 3j plus 1 c. And one more. Good. Now over here in the corner, let's work out something that you may have seen in a basic calculus class, but I think often I would have forgotten this formula for sure. So if I want the first derivative of f at x, I can say that this is approximately equal to f of x plus epsilon minus f of x over epsilon. If I want the second derivative of x, well, I'm definitely allowed to actually switch to the other definition of the first derivative. So I can look at f prime at x minus f prime at x minus epsilon over epsilon. And now, if I stick this first formula into this second formula, this should have been an approximate, good. Then I find that f double prime of x is approximately equal to, well, I'll get an f of x plus epsilon here, then a minus f of x, then a minus f of x plus epsilon minus epsilon, so just a minus f of x, and then a minus f of x minus epsilon. But notice that the two f of x's in the middle combine. So I get f of x plus epsilon minus 2 f of x, and then minus minus, so plus f of x minus epsilon, and all over epsilon squared. Great. And what that means is that this thing here, which has the same pattern, 1 minus 2, 1, looks precisely like the second x derivative, or the second spatial derivative of u. But with this c in here having been multiplied over. So this gives us, is basically approximately equal to, I guess I'll say, c squared over 6 tau times the x derivative, the second x derivative of u at t tau 3j c. Awesome. But notice that up here, this was approximately equal to the t derivative of u, again at t tau 3j c. Wonderful. So look, in this case where we had 3j c, we have an equation that relates these two things. So the partial t, I guess. I'm kind of having t do double duty, which is unfortunate, but it's all right. And now let me just say tx. Doesn't really matter since the arguments were the same in both. Wonderful. Now, you might think, okay, but I cheated because I picked the one with the easier transformation rules, right? This one has a much more complicated transformation pattern. So let's see what happens there. The answer is that it won't be super different. We want to do the exact same thing that we did here. So let's do that. U of t plus 2 tau 3jc minus u of t. Oh, I'm actually realizing I need to correct an error down here. before I continue. So I forgot my constant here, 6 tau. And we have to make an assumption here. It certainly could be the case that since xi is very small and tau is very small, one or the other of them could be much smaller than the other one. So it could be that this is either an infinite looking quantity or a zero looking quantity. Basically, we only get interesting behavior in the case where this quantity is, we would say, O1. In other words, is just a sort of normal scale number. This will in fact set the scale in part for the problem. So that's where we need this requirement to come in. Okay, let me continue up here with our second case. So minus u t tau 3, oh, and I'm copying things wrong as well. 3j plus 1 xi, here we go. 3j plus 1 xi, good, over 2 tau. Excellent. And then I just need to stick this in. So let me pull out my 1/6 so that I'll get a 12 in the bottom. And then I'll just multiply this by 6. So this is going to equal 1 over 12 tau times the sum from k is equal to 3j minus 1 up to 3j plus 4 of u t tau k xi. And maybe I need a second parenthesis, set of parentheses maybe. Okay, and then minus minus 6 u t tau 3j plus 1 xi. Excellent. Okay, so here something much more sort of odd is happening, which is that now we have a sum of 6 terms, and then we have 6 different values of u to worry about. So what are we going to do? How is this going to work? The answer is basically that we need to think about this term by term. So 3j minus 1, sorry, 3j, so yeah, I guess let's list all of them. 3j minus 1, 3j, 3j plus 1, 3j plus 2, 3j plus 3, 3j plus 4. Those are our 6 values. And we know that this is the one that we're going to be able to sort of take out, or that we're going to be able to alter using this thing. And if we just did it without doing any sort of modification, we would of course get that all of these had sort of a 1/12 attached to them. And then this one would have a minus 5 attached to it. And it's not going to be easy to sort of decouple that. We could do it. It would be a lot of work and might involve some higher derivatives, but we're not going to. What we're instead going to do is utilize the fact that we assume that as we take these things to be very small, our function u of t and x that we see here is going to be continuous, which means that the difference between the value of the function at consecutive points is not going to be very large. So what we're actually going to do is split this into 3 approximate terms. So we're going to say that 6u of t tau, 3j plus 1 xi, is approximately equal to u of t tau, sorry, 2u of t tau. The first one that we'll want is 3j xi. Okay, then plus 2 u t tau. The next one that we'll want is 3j plus 2t. Or maybe we want to split them. Oh, yeah. Sorry, we want to split them into groups of 3. Just like we did over here. Excellent. So 3j, and then the other one we want is 3j plus 3. Wonderful. Okay, and once we've done that, the process is actually exactly the same as what we've seen here. So I'm not going to carry it through all the way to the end. What we get in the end is just another equation just like this. So what we find is that the time derivative, the first time derivative of u, which is now a function of t and x, is equal to some constant times the second, yes, the second spatial derivative of u. And moreover, we actually do know one more thing. Even though we couldn't figure out the scale of this and had to just input that the scale was this in order for us to get useful or interesting behavior, we do know that the sign is positive, since c is positive and tau is positive. So here we have d is greater than 0. D is often used as the name for the constant here. Obviously, it's not great. I don't love it because D often has some sort of differential meaning, but I'll keep it in here just for sort of reference clarity's sake. Okay, so that's it for this video. In the next video, we're going to look at a different way of getting this exact same kind of behavior, but in a more, maybe a cleaner way. I'm excited to show you how that works. I'll see you in the next one.